The second major group of the insecticides, the alkyl or organic phosphate, are among the most poisonous chemicals in the world. The chief and most obvious hazard attending their use is that of acute poisoning of people applying the sprays or accidentally coming in contact with drifting spray, with vegetation coated by it, or with a discarded container. In Florida, 2 children found an empty bag and used it to repair a swing. Shortly thereafter, both of them died and 3 of their playmates became ill. The bag had once contained an insecticide called parathion, one of the organic phosphate. Test established death by parathion poisoning. On another occasion, 2 small boys in Wisconsin, cousins, died on the same night. One had been playing in his yard when spray drifted in from an adjoining field where his father was spraying potatoes with parathion. The other had run playfully into the barn after his father and had put his hand on the nozzle of the spray equipment. The origin of these insecticides has a certain ionic significance. Although some of the chemicals themselves, organic esters of phosphoric acid, has been known for many years, their insecticidal properties remain to be discovered by a German chemist, Gerhard Skrelder, in the late 1930s. Almost immediately, the German government recognized the value of these same chemicals as new and devastating weapon in man's war against its own kind, and the work on them was declared secret. Some became the deadly nerve gases. Others of closely allied structure became insecticides. The organic phosphorus insecticides act on the living organism in a peculiar way. They have the ability to destroy enzymes that perform necessary functions in the body. Their target is the nervous system, whether the victim is an insect or a warm-blooded animal. Under normal conditions, an impulse passes from nerve to nerve with the aid of a chemical transmitter called acetylcholine, a substance that performs an essential function and then disappears. Indeed, its existence is so ephemeral that medical researchers are unable, without special procedures, to sample it before the body has destroyed it. This transient nature of the transmitting chemical is necessary to the normal functioning of the body. If the acetylcholine is not destroyed, as soon as the nerve impulse has passed, impulses continue to flash across the bridge from nerve to nerve, as the chemical exerts its effects in an even more intensified manner. The movements of the whole body become uncoordinated. Tremors, muscular spasms, convulsions, and death quickly result. This contingency has been provided for by the body. A protective enzyme called cholinesterase is at hand to destroy the transmitting chemical once it is no longer needed. By this means, a precise balance is struck and the body never builds up a dangerous amount of acetylcholine. But in contact with the organic phosphorus insecticides, the protective enzyme is destroyed, and as the quantity of the enzyme is reduced, that of the transmitting chemical builds up. In this effect, the organic phosphorus compounds resemble the alkaloid poison muscarine found in a poisonous mushroom, the fly amanita. Repeated exposures may lower the cholinesterase level until an individual reaches the brink of acute poisoning, a brink over which he may be pushed by a very small additional exposure. For this reason, it is considered important to make periodic examinations of the blood of spray operators and others regularly exposed. Parathion is one of the most widely used organic phosphate. It is also one of the most powerful and dangerous. Honeybees become widely agitated and bellicose on contact with it, perform frantic cleaning movements, and are near death within half an hour. A chemist thinking to learn by the most direct possible means the dose acutely toxic to human beings, swallowed a minute amount, equivalent to about 0.002424 ounce. Paralysis followed so instantaneously that he could not reach the antidotes he had prepared at hand, and so he died. Parathion is now said to be a favorite instrument of suicide in Finland. In recent years, the state of California has reported an average of more than 200 cases of accidental parathion poisoning annually. In many parts of the world, the fatality rate from parathion is startling. 100 fatal cases in India and 67 in Syria in 1958 and on average of 336 deaths per year in Japan. Yet, some 7 million pounds of parathion are now applied to the fields and orchards of the United States by hand sprayers, motorized blowers and dusters, and by airplane. The amount used on California farms alone could, according to one medical authority, provide a lethal dose for 5 to 10 times the whole world's population. One of the few circumstances that save us from extinction by this means is the fact that parathion and other chemicals of this group are decomposed rather rapidly. Their residues on the crops to which they are applied are therefore relatively short-lived compared with the chlorinated hydrocarbons. However, they last long enough to create hazards and provide consequences that range from the merely serious to the fatal. In Riverside, California, 11 out of 30 men picking oranges become violently ill, and all but one had to be hospitalized. Their symptoms were typical of parathion poisoning. The group had been sprayed with parathion some 2.5 weeks earlier. The residues that reduced them to retching, half-blind, semi-conscious misery were 16 to 19 days old. And this is not by any means a record for persistence. Similar mishaps have occurred in groups sprayed a month earlier, and residues have been found in the peel of oranges 6 months after treatment with standard dosages. The danger to all workers applying the organic phosphorus insecticides in field, orchards and vineyards is so extreme that some states using these chemicals have established laboratories where physicians may obtain aid in diagnosis and treatment. Even the physicians themselves may be in some danger unless they wear rubber gloves in handling the victims of poisoning. So may a lender is washing the clothing of such victims which may have absorbed enough parathion to affect her. Malathion, another of the organic phosphate, is almost as familiar to the public as DDT, being widely used by gardeners in household insecticides, in mosquito spraying, and in such blanket attacks on insects as the spraying of nearly 1 million acres of Florida communities for the Mediterranean fruit fly. It is considered the least toxic of this group of chemicals, and many people assume they may use it freely and without fear of harm. Commercial advertising encourages this comfortable attitude. The alleged safety of malathion rests on rather precarious ground, although as often happens, this was not discovered until the chemical had been in use for several years. Malathion is safe only because the mammalian liver, an organ with extraordinary protective powers, renders it relatively harmless. The detoxification is accomplished by one of the enzymes of the liver. If, however, something destroys this enzyme or interferes with its action, the person exposed to malathion receives the full force of the poison. Unfortunately for all of us, opportunities for this sort of thing to happen are legion. A few years ago, a team of Food and Drug Administration scientists discovered that when malathion and certain other organic phosphates are administered simultaneously, a massive poisoning results up to 50 times as severe as would be predicted on the basis of adding together the toxicities of the two. In other words, of the lethal dose of each compound may be fatal when the two are combined. This discovery led to the testing of other combination. It is now known that many pairs of organic phosphate insecticides are highly dangerous, the toxicity being stepped up or potentiated through the combined action. Potentiation seems to take place when one compound destroys the liver enzyme responsible for detoxifying the other. The two need not be given simultaneously. The hazard exists not only for the man who sprays this week with one insecticide and next week with another. It exists also for the consumer of sprayed products. The common salad bowl may easily present a combination of organic phosphate insecticides. Residues well within the legally permissible limits may interact. The full scope of the dangerous interaction of chemicals is as yet little known, but disturbing findings now come regularly from scientific laboratories. Among these is the discovery that the toxicity of an organic phosphate can be increased by a second agent that is necessarily an insecticide. For example, one of the plasticizing agent may act even more strongly than another insecticide to make malathion more dangerous. Again, this is because it inhibits the liver enzyme that normally would draw the teeth of the poisonous insecticide. What of other chemicals in the normal human environment? What in particular of drugs? A bare beginning has been made on this subject, but already it is known that some organic phosphate increase the toxicity of some drugs used as muscle relaxants, and several others markedly increase the sleeping time of barbiturates. In Greek mythology, the sorceress Medea, enraged at being supplanted by a rival for the affections of her husband Jason, presented the new bride with a robe possessing magic properties. The wearer of the robe immediately suffered a violent death. This death by indirection now finds its counterpart in what are known as systemic insecticides. These are chemicals with extraordinary properties which are used to convert plants or animals into a sort of Medea's robe by making them actually poisonous. This is done with the purpose of killing insects that may come in contact with them, especially by sucking their juices or blood. The world of systemic insecticides is a weird world, surpassing the imaginings of the Brothers Grimm, perhaps most closely akin to the cartoon world of Charles Addams. It is a world where the enchanted forest of the fairy tales has become the poisonous forest, in which an insect that chews a leaf or sucks the sap of a plant is doomed. It is a world where a flea bites a dog and dies because the dog's blood has been made poisonous, where an insect may die from vapors emanating from a plant it has never touched, where a bee may carry poisonous nectar back to its hive and presently produce poisonous honey. The entomologist's dream of the built-in insecticide was born when workers in the field of applied entomology realized they could take a hint from nature. They found that wheat growing in soil containing sodium selenate was immune to attack by aphids or spider mites. Selenium, a naturally occurring element found sparingly in rocks and soils of many parts of the world, thus became the first systemic insecticide. What makes an insecticide a systemic is the ability to permeate all the tissues of a plant or animal and make them toxic. This quality is possessed by some chemicals of the chlorinated hydrocarbon group and by others of the organophosphorus group, all synthetically produced as well as by certain naturally occurring substances. In practice, however, most systemics are drawn from the organophosphorus group because the problem of residues is somewhat less acute. Systemics act in other devious ways. Applied to seeds, either by soaking or in coating, combined with carbon, they extend their effects into the following plant generation and produce seedling poisonous to aphids and other sucking insects. Vegetables such as peas, beans, and sugar beets are sometimes thus protected. Cotton seeds coated with the systemic insecticides have been in use for some time in California, where 25 farm laborers planting cotton in the San Joaquin Valley in 1959 were seized with a sudden illness caused by handling the bags of treated seeds. In England, someone wondered what happened when bees made use of nectar from plants treated with systemics. This was investigated in areas treated with a chemical called scaradine. Although the plants had been sprayed before the flowers were formed, the nectar later produced contained the poison. The result, as might have been predicted, was that the honey made by the bees also was contaminated with scaradine. Use of animal systemics has concentrated chiefly on the control of cattle grub, a damaging parasite of livestock. Extreme care must be used in order to create an insecticidal effect in the blood and tissues of the host without setting up a fatal poisoning. The balance is delicate, and the government veterinarians have found that repeated small doses can gradually deplete an animal's supply of the protective enzyme colon esterase, so that without warning a minute additional dose will cause poisoning. There are strong indications that fields closer to our daily lives are being opened up. You may now give your dog a pill which it is claimed will rid him of fleas by making his blood poisonous to them. The hazards discovered in treating cattle would presumably apply to the dog. As yet, no one seems to have proposed a human systemic that would make us lethal to a mosquito. Perhaps this is the next step. So far in this chapter, we have been discussing the deadly chemicals that are being used in our war against the insects. What of a simultaneous war against the weeds? The desire for a quick and easy method of killing unwanted plants has given rise to a large and growing array of chemicals that are known as herbicides, or less formally as weed killers. The story of how these chemicals is used and misused will be told in chapter 6. The question that here concerns us is whether the weed killers are poisonous and whether their rise is contributing to the poisoning of the environment. As a spray applied to potato fields to destroy the vines, they have taken a toll of human and non-human life. In England, this later practice developed about 1951 as a result of a shortage of sulfuric acid formerly used to burn off the potato vines. The Ministry of Agriculture considered it necessary to give warning of the hazard of going into the arsenic sprayed fields, but the warning was not understood by the cattle, and reports of cattle poisoned by the arsenic sprays came with monotonous regularity. The legend that the herbicides are toxic only to plants and so pose no threat to animal life has been widely disseminated, but unfortunately it is not true. The plant killers include a large variety of chemicals that act on animal tissue as well as on vegetation. They vary greatly in their action on the organism. Some are gentle poisons, some are powerful stimulants of metabolism, causing a fatal rise in body temperature. Some induce malignant tumors either alone or in partnership with other chemicals. Some strike at the genetic material of the race by causing gene mutations. The herbicides, then like the insecticides, include some very dangerous chemicals, and their careless use in the belief that they are safe can have disastrous results. Despite the competition of a constant stream of new chemicals issuing from the laboratories, arsenic compounds are still liberally used, both as insecticides and as weed killers, where they usually take the chemical form of sodium arsenite. The history of their use is not reassuring. As roadside sprays, they have caused many a farmer, his cow, and killed the uncounted number of wild creatures. As aquatic weed killers in lakes and reservoirs, they have made public waters unsuitable for drinking or even for swimming. When death came also to a farmer's wife through arsenic contaminated water, one of the major English chemical companies stopped the production of arsenical sprays and called in supplies already in the hand of dealers, and shortly thereafter the Ministry of Agriculture announced that because of high risk to people and cattle, restrictions on the use of arsenides would be imposed. In 1961, the Australian government announced a similar ban. No such restriction impeded the use of these poisons in the United States, however. Some of the D-nitro compounds are also used as herbicide. They are rated among the most dangerous materials of this type in use in the United States. D-nitrophenol is a strong metabolic stimulant. For this reason, it was at one time used as a reducing drug, but the margin between the sliming dose and that the required to poison or kill was slight. So slight that several patients died and many suffered permanent injury before use of the drug was finally halted. A related chemical, pentachlorophenol, sometimes known as penta, is used as a weed killer as well as an insecticide, often being sprayed along railroad tracks and in waste areas. Penta is extremely toxic to a wide variety of organisms from bacteria to man. Its fearful power is illustrated in a fatal accident recently reported by the California Department of Health. A tank truck driver was preparing a cotton defoliant by mixing diesel oil with pentachlorophenol. As he was drawing the concentration chemical out of a drum, the spigot accidentally toppled back. He reached in with his bare hand to regain the spigot. Although he washed immediately, he became acutely ill and died the next day. While the results of weed killers such as sodium arsenite or the phenols are grossly obvious, some other herbicides are more insidious in their effects. For example, the now famous cranberry weed killer, aminotriazole or amitrole, is rated as having relatively low toxicity, but in the long run, its tendency to cause malignant tumors of the thyroid may be far more significant for wildlife and perhaps also for man. Among the herbicides are some that are classified as mutagens, are agents capable of modifying the genes, the materials of heredity. we are rightly appalled by the genetic effects of radiation. How then can we be indifferent to the same effect in chemicals that we disseminate widely in our environment?